Thanks for tuning in. This video demonstrates SDM's disk encryption capability. Since this is about disk burning and encryption, preparation of the image, which is simply using SDM to customize the image, won't be covered. I'm going to use a standard RasPiOS ARM64 Lite image on which I have run some basic customization. Of course, this can be used on desktop versions as well. This demo will show you a few key features of SDM's disk burn capabilities. After the disk is burned, we'll boot it and watch the encryption process of both the rootfs and a separate data partition that we create during the burn. Once the burn process has completed, the boot disk will have a GPT partition table. The boot partition will be as it always is. The rootfs will use the BTRFS file system and it will be encrypted. Of course, X4 file system is supported as well. A third partition, which we create during the burn, will be encrypted and use the BTRFS file system also. One last note, I've edited out long waits. While the process is fairly quick, it's not quite as quick as shown in this video. To give you an idea of the wait time, the original unedited video is about 8.5 minutes to both burn and fully encrypt the rootfs and data partition. This video is less than 6 minutes. SDM simplifies and automates RasPiOS customization. It has a broad set of capabilities to help you manage your Pi fleet. If you're watching this video, you probably don't need an overview of SDM, but if you do, head over to the SDM GitHub or watch my video on getting started with SDM. Most SDM functionality is implemented via plugins. Plugins help you configure your RasPiOS system the way you want it. You'll see the use of several plugins in this video. The first step is to create a couple of key files that we'll use to unlock the encrypted partitions. It's certainly possible to use the same key file for both partitions, but we'll use two different key files for this demo. The first command initializes the USB key disk and creates the first key. The next command adds a second key to that already created key disk. We'll use those key files in the burn command you'll see next. In addition to key files, SDM supports passphrase unlock for both partitions. Also, the root partition can be unlocked with a YubiKey. Here's the script and the plugins that we'll use for burning the disk. I want to call your attention to a couple points. We'll burn the rootfs with the BTRFS file system. After the bootfs and rootfs partitions are copied, we'll run the plugin specified in the plug file burn file. The first plugin is the cryptroot plugin, which configures the system to enable the rootfs encryption process. I've also configured it to include passphrase unlock via SSH, although we won't be using that in this demo. And the cryptroot plugin and the cryptpart plugin are independent. Neither one requires the other. The SSH host key plugin generates the SSH host keys for the new system as part of the burn, rather than waiting until the system first boot. There's likely to be more system entropy now as compared to during system boot. Secure SSH key generation requires high-quality system entropy or randomness. Alternatively, SDM's first boot service will generate the SSH keys during the first system boot, and it generally works fine. The copy file plugin copies the data partition encryption key from the host onto the just burned disk, so it's available to the cryptpart plugin later in the process. The next three plugins are a bit special. Defer plugins are run after the encryption process has completed, or on the reboot after the first system boot if not doing encryption. The first of these encrypts the third partition, which we created during the disk burn, and formats it with the BTRFS file system. The second of these runs a command to wait for a minute in case I have anything smart to say after the process is nearly complete, and the third reboots the system. I also want to highlight the parted plugin, which is a special purpose plugin known as a burn plugin. Burn plugins are run during the burn process after regular plugins and have access to the burn disk as a device. The parted plugin here will extend the rootfs by 8 GB. It will also create a third partition that consumes the remainder of the disk, but does not put a file system on it. The CryptPart plugin takes care of the file system later. Lastly, I shortened the file names so they would fit on this slide. They are unmodified in the video, of course. Okay, let's start the burn process. Now we're ready to boot the disk. To put the timing in perspective, the entire encryption process shown here, including encrypting rootfs and the data partition, took about 7 minutes on an 8GB Pi 5. The code that encrypts the rootfs normally uses a scratch disk to save and restore rootfs. However, if the rootfs is small enough, as this one is, a RAM disk will be used instead, which of course reduces the time dramatically. This process would take several minutes longer if the rootfs is too large for the RAM disk optimization. Total time required is dependent on the speed of the disk we're encrypting, the scratch disk, and the processor speed. The system will reboot here. If we weren't doing the encryption process, the system would then be ready for normal operation. But we are doing encryption, so the system will start up normally, but a service created by the cryptroot plugin will run at the completion of the next startup instead of dropping to a command prompt. This service configures the system to start the encryption process by running encryptconfig. Here we'll see encryptconfig run. In the background, it is installing any packages needed for the encryption process and updating and configuring the system to boot once the rootfs is encrypted. As the system reboots, the rootfs is inaccessible due to the way the system is configured, so the system will drop into the initramfs. Now we'll run the rootfs conversion script. encryptfs saves a copy of the rootfs partition either to a RAM disk or the scratch disk depending on the size of the rootfs and memory. It then encrypts the rootfs partition, overwriting the prior rootfs with the LUX encryption configuration. Next, encryptfs unlocks the encrypted partition and then restores the saved rootfs partition data into the now encrypted partition on the boot disk. As you will see, this example uses a RAM disk and it's quite fast. At this point, the encryption process is complete. Typing exit here will continue the system boot that's already in progress. Yep, the one where the system couldn't find its rootfs. The system will now find its rootfs and go through the remainder of the boot process. The final step in the rootfs encryption process is the service encryptfs cleanup, which completes the rootfs encryption configuration by configuring initramfs for normal operation. The system will then reboot one last time. The rootfs unlock script, which was put into the initramfs by encryptconfig, locates the key file disk and provides the key file contents to the code that unlocks the rootfs and continues the boot. You'll notice that the SSH server is also started since I configured it in. If we weren't also encrypting a data partition, we'd be all done and the system would be ready to go when this boot completes. But since we are encrypting a data partition, this will be done as the system boot completes via the defer plugin we set up when we burned the disk. Now we'll log in and first take a look at the system journal, and then we'll watch as new entries are written to the log so that you can see what this looks like. I use JC as an alias for journal control. Now we'll wait 60 seconds and then we'll reboot the system one last time. The crypt_part plugin has encrypted the requested partition and created a file system on it. When the system reboots, the USB key disk will be found and the rootfs will be automatically unlocked. Then, farther along in the boot process, systemd crypt setup will automatically mount the key disk, unlock the data partition, and then unmount the key disk. Now we'll reboot one last time and then have a look at the encryption configuration. As you can see, DF shows two encrypted partitions, the rootfs, which is crypt root, and the data partition, data part. Looking at Crypt tab, you can see the configuration for the encrypted partitions and how they're mounted in FS tab, thanks to the handiwork of the crypt root and crypt part plugins. That's it for this demo. I hope you found it useful. If you have any questions, please head over to the SDM GitHub and post them. I'm happy to help people get started with SDM or become more proficient with its many capabilities.